Okay, so here's part 2, dealing with problem number 4. And so this problem is a little bit different than problem number 3 is, because if you read it, like you should always do first and foremost, it says, if 0.5 moles of NO2 is placed in a 2-liter flask to create NO and O2, calculate the equilibrium concentrations if K equals 1.2 times 10 to the negative fifth. So right off the bat, it tells you what KEQ is. It gives you KEQ. It does not give you any initial concentrations directly. What it does give you is it gives you how many moles here in how many liters. So you need to figure out your initial concentration of NO2 using molarity. So there are 0.5 moles in 2 liters. So off to the side, and I'm just going to do this over here, you have your 0.5 moles in every 2 liters. And once you do that division, you'll figure out that there is 0.25 molarity, or 0.25 moles in every 1 liter. So we just do that division, 0.25 with our capital M. And that is how much NO2. That's our concentration of NO2 initially. And you know it's initial because it says, hey, this many moles is placed in a flask. So initially you've placed this in, nothing else has happened. And then you are also going to write out, if it's not already given to you, this expression. But this expression is given to you. Congratulations, you didn't actually have to write it out, but you look at it. Is it balanced? Looking at it, 2 ends on this side, 2 ends on that side, 4 O's on this side, 2 4 O's on that side. Congratulations, we are balanced. And then you are going to go ahead and you're going to write out your roadmap equilibrium expression. So your KEQ, or your 1.2 times 10 to the negative fifth, equals your products over your reactants. So there's your blank one. We fill in our products here. So our first product is our NO. There is a coefficient in front of that NO, so we're going to go ahead and raise that to the power of 2. There is no coefficient in front of our O2, so that gets left alone. And we have our NO2 down here. There is a coefficient, so we raise that to the power of 2 as well. So this is your template. Now we go ahead and we draw our ice table. So here's your ice table. And we can fill in our initial concentrations, because recall once again, I stands for initial, C stands for change, and E stands for equilibrium. So we know what our initial concentration of NO2 was because we figured it out over here. So we fill in our 0.25 right here. This problem does not give us any initial concentrations for NO or for O2. But you can use your logic skills to figure out what the initial concentrations of those are going to be. Because if you've literally just dropped a sample of NO2 into a container and done nothing else, initially, before the reaction happens, you're not going to have any product because nothing's reacted yet. So your initial concentrations, you're going to assume right now, are 0 for NO and for NO2. Now, the second thing that you're going to do is you're going to fill in your change for this one. And the reason you're going to do that is because, once again, you are making some assumptions. Recall back when we did the activity on Friday, and I put all the paper balls on one side of the room and I told you guys to start. Initially, you threw, like each one of you, at least the ones that were participating, you all picked up a paper ball and you threw it all the way to the product side. And all of those paper balls had to get to the product side before they could turn back into reactants. So the exact same thing is going to happen here in the change column. So logically speaking, you don't know the exact concentration that's changing because you don't know the end concentrations. You don't know the equilibrium concentrations yet for each one individually. So once again, you have your X being your change. But to know how much of X, how many molar equivalents of X, you look at your coefficients up here. So logically, we are going to say, hey, if we're starting out with 100% of reactants, then logically all that has to turn into product before it can start turning back into reactants. So we're going to say minus 2x here. That's minus. Make that darker. And you say minus because this is going to turn into a product. So whatever concentration you had is going to get subtracted and go over there. And you know that it's a 2 because of this coefficient there. So logically, again, if we're turning that into products and there's a coefficient of 2 right here, you're going to say, okay, well, plus 2x here. And you're going to have a plus x there because there is no coefficient up here, so this is just going to be x. Because you don't know how much you're adding. You don't know what the concentration of x is. It's an unknown right now. And then for our equilibrium boxes on the bottom, all you have to do is you have to total those. So if we total these two columns, we have 0.25 minus 2x. So 0.25 minus 2x. We total these two, 0 plus 2x, so this is just plus 2x here. And we just have an x here, positive x, because we've added 0 and x. And that's your ICE table. Now what you have to do is you have to make a couple of other assumptions when you are filling in your equilibrium expression over here. So once again, you're going to rewrite your KEQ just like we did up here in problem 3, except you have a number for it now. So your number is your 1.2 times 10 to the negative 5th. And you're going to start filling in numbers for all these up here. So your NO concentration, if you go to that column, you go all the way down to equilibrium, that is 2x. And we are going to raise that to the power of 2 because up in our roadmap expression, we did that up here. And we have our O2 concentration, which is x here. X over our NO2 concentration raised to the power of 2. Now this one, slightly more complex. We have our 0.25 minus 2x raised to the power of 2. Now, here's where you have to start making some assumptions. So if you watch the video for small x approximations, you should have an idea of what I'm about to do. But for those of you that haven't, you're going to compare your initial concentration of your NO2 that was given to you indirectly, but it was given, and you're going to compare your equilibrium constant. So we're comparing our 1.25 times 10 to the negative 5th, and we're comparing 0.25. And when we do that, we're going to notice that 1.25 times 10 to the negative 5th is a lot smaller than 0.25 by approximately 4 factors of 10. Meaning that if you were to write this out longhand, it would be 0.00012, which is, again, a lot smaller than this. And what that tells you is when you are subtracting 2x, it's asking you to assume that x is very small, because if this equilibrium constant, what is changing, is very, very, very tiny, it means that you're going to have more reactant at equilibrium than product. So this concentration, this initial, is not going to change by a lot. So you assume that this is very near 0 because it didn't change a whole heck of a lot. So what we do in that instance is we just cross it out, or we don't even deal with it because it's going to change by what, 0.0001, and that's not going to affect it. So it's going to basically just be 0.25 squared down here, which makes it a lot easier for us to solve that problem. So now all we have to do is we have to rewrite our expression. We simplify it a little bit. So we end up on this side. If we simplify this, we go 2x squared times x. So that ends up being 4x cubed. If we simplify that and we multiply 1.2 times 10 to the negative fifth times 0.25 squared to move that over there, and we end up with 7.5 times x to the negative seventh. Or not times x to the negative seventh, times 10 to the negative seventh. I apologize. So this is our simplified expression, and we solve for x. So I'm just going to do that right over here. X turns out to be 5.72 times 10 to the negative third, or 0.00572. So this is the concentration that is changing. So to put that in perspective for you, I'm saying that between initially dropping NO2 into a container and when that reaction reaches equilibrium, you have 0.25 moles minus 0.00572 times 2. So minus 0.01 effectively at equilibrium. And so you basically have most of your reactant left at equilibrium. And you only have 0.01 moles of NO and 0.00572 moles of oxygen at equilibrium. So over here, when you figure out all your answers, you have your molarity of your NO2, your concentration of that. Once again, that is going to be your 0.25 minus 2 times this, because this is your x, and so that's going to be 0.24 m. You have your nitrogen monoxide, your NO, so your concentration of that at equilibrium is your 2x, your 2 times this, which is approximately 0.011 molarity. And you have your oxygen concentration, which is just X. So your oxygen concentration at equilibrium is just this. So 0.005, we'll round that to 0.0057 molarity, based on all the assumptions that you've made. And that is how you do a small x approximation. But once again, if you were confused by this explanation, I urge you to go and watch the videos for small and large x approximation, because they can only help you. So I hope that was helpful for you, and I hope the rest of this worksheet is a little bit easier now that we've gone over that. Have a good day. Stay safe.